All right, in this video, we're going to find some Taylor series from other Taylor series like we've done before, except the difference here is we're going to integrate the previous Taylor series we know to derive the Taylor series for other functions. And the first function I want us to do is the function just ln of 1 plus x. So we're going to think about how we can integrate already known Taylor series to basically give us that ln of 1 plus x. And this is going to be a multi-step problem for us. And where this problem starts is with our first power series representation of a function we ever learned, the 1 over 1 minus x, which was equal to the infinite series of x to the n, from n equals 0 to infinity. And remember, we introduced that stenciling idea, so wherever there was that x, we would just replace that with open parentheses in both of these sides. And the reason why we want to go ahead and do this is, well, we're going to go ahead and integrate not the function 1 over 1 minus x, but the function 1 over 1 plus x. So if we start off with a 1 over 1 plus x, we can use that exact stenciling idea where inside of that parenthesis, we can just write a minus x. So in that denominator, we have a 1 minus a minus x, so 1 plus x, which means on the far right in our series, we can just put a minus x inside of those parentheses. So what this series actually looks like for 1 over 1 plus x is a nice reminder, is the infinite series from n equals 0 to infinity of minus 1 to the n times x to the power of n. And well, why would we want to do that? And well, this is step 2 for this process. If we have this relationship of 1 over 1 plus x equaling that power series of minus 1 to the nth power times x to the power of n, well, we can come across and integrate both sides of this equation. And if we integrate both sides of this equation, that left-hand side, the integral of 1 over 1 plus x, well, that gives us the ln of 1 plus x. So that's where this ln is actually coming from, and it's equal to whatever that antiderivative of the right-hand side is. So again, we're doing this integral. We're going to use the antiderivative power rule in a moment, but that integral sign passes by the negative 1 to the n, passes by the summation, and it's just going to act on that x to the nth power, because again, that's the only thing with x dependence inside of that summation. So when we go ahead and integrate this, the left-hand side is still ln of 1 plus x, and well, that right-hand side now is by power rule, we bump up that power plus 1, which means we have x to the power of n plus 1 all over that power plus 1, which means we divide by n plus 1 as well. And because this was an indefinite integral, we add plus c. And this is how we can get a power series representation or Taylor series representation for the ln of 1 plus x. So we just had to be a little bit clever of what function we were integrating in order to get that function we cared about. And we're going to do a similar thing for this next example, in which the function we want to find its Taylor series for is maybe a scary-ish looking function, but this is the arctangent of x. And we're going to do this in a couple similar steps. We're also going to start off with the power series for 1 over 1 minus x. So just to remind us, that is the relationship we had before. So this is kind of step 1. The second step was we make a stencil of this thing, but where we're actually going is we want to find the power series for 1 over 1 plus x squared. So again, we're trying to put this in the form of 1 minus a quantity, because then we can just use our stenciling idea that we used previously throughout this unit. Oops. So anywhere there is an x, we can replace that with open parentheses. So if we're trying to get that into the form up above, in that denominator, we could write this as 1 minus, and then parentheses, a minus x squared. And we can put that into the right-hand side as well inside of that power series. So this was our power series for the function 1 over 1 plus x squared. And well, why are we doing that? And the whole reason we're doing that is because the antiderivative of 1 over 1 plus x squared is arctangent. So again, we're starting off with 1 over 1 plus x squared. It equals that power series that we found up above. And I'll just rewrite this as a minus 1 to the n times x to the 2n over here. And what we can do to get the arctangent is integrate both sides, because the integral of that left-hand side is just our arctangent function. And whatever's on that right-hand side is now the arctangent's power series or Taylor series representation. So again, that integral is only going to affect stuff that has x dependence. So it passes by the summation, it passes by that negative 1 to the n, and it's just going to affect the x to the power of 2n. So if we do this integral by the antiderivative power rule, what we find is the arctangent's power series representation is equal to the series from n equals 0 to infinity of minus 1 to the n. And then we do the antiderivative power rule. We bump up that power plus 1, so we get x to the 2n plus 1, and we divide by that power plus 1 as well. I guess I don't technically need that parenthesis down there. And then, of course, we have plus c, because that's an indefinite integral. And that would be our power series. But actually, we could do a little bit better than that, because we can actually figure out what c is in this case. So for example, because we need the left-hand side to equal the right-hand side for all values of x, if you remember, the arctangent, its domain is all real numbers. Or in other words, we can put in any number x between positive and negative infinity, and that left-hand side is happy to accept it, which means the right-hand side must also have a domain of all real numbers. But in particular, one of those numbers is actually going to be very nice for us to figure out what that plus c is. So for example, if we evaluate the arctangent of 0, I can just put 0 into that sum wherever there's an x. And well, what that's going to do for us is basically cancel out that entire series entirely. So because we're raising 0 to some power 2n plus 1 in every single term of that series, and that power is never a 0, so we never have 0 raised to the 0th power, that whole series is equal to 0, but the arctangent of 0 is 0 itself, which means that c in this case must be actually equal to 0. And there's one reason why I'm going this extra step beyond what we've done previously in class when finding antiderivatives or taking the integral of some of these Taylor series. And that's because we can actually use this arctangent for something interesting. Right, so just to be clear, we literally found that the value of c must be 0 in this particular case, and that the arctangent has this particular power series or Taylor series representation. Now, what's particularly interesting about this is we can put in different values of x into the left and right side, and we might find some interesting relations. So for example, if I do x equals 1, we have that the arctangent of 1 is equal to, well, that series we just found, from n equals 0 to infinity of -1 to the n times, well, 1 raised to the 2n plus 1 power, which that is always just going to give us a 1 in that numerator, all divided by 2n plus 1. Why is this interesting? Well, the arctangent of 1 is equal to pi over 4. The other thing, this 1 raised to the power of 2n plus 1, it's always going to be equal to 1. So in other words, we found a series that presumably should converge to pi. So what we found was pi over 4 is equal to the infinite series from n equals 0 to infinity of -1 to the n all over 2n plus 1. So if we just multiply both sides by 4, we find that pi is equal to 4 times the infinite series from n equals 0 to infinity of -1 to the n all over 2n plus 1. So we can find some interesting series that converge to pi using this arctangent.